Section 3.3 is on displaying qualitative data graphically. May have been the same thing we wrote down earlier. Alright, so one way to display data is a bar chart. And a bar chart is a simple graphical display in which the length of each bar corresponds to the number of observations in a category. Corresponds to the number of observations in a category. So pretty straightforward. One type of bar chart is called a stacked bar chart. And stacked bar charts are bar charts where different subcategories are stacked on top of each other. Alright, so your book does have a lot of different bar charts. I can show you an example of just a regular bar chart and a stacked bar chart real quick. I'm sure that everyone in here knows what a bar chart looks like, and it's whether you've ever used one or not, I'm sure that you've seen them. It's a very common way of representing data. Alright, so here's an example of a bar chart. Your book will sometimes go through the actual data, but this is what it would look like once it was represented, as a bar chart. You see this is dollar sales in thousands, sales reports, and then these are the salespeople here. And so this is how much they've sold. And in my opinion, this bar chart is a little misleading because you see Susan here, she sold between 185 and 190,000, and Beth sold between 205 and 210,000. So, let's think about that for just a second. Susan sold, if I had to guess, let's just guess that Susan sold about 187,500. That's why, that would be the midpoint here between these two. So let's say that that's what Susan sold. And then Beth, if she sold the midpoint between these two values, that means she sold about 207,500. And while 207,000 is, considerably in dollars, is a large amount, maybe that's 30,000 more. But if we just were to skim over this bar chart and not pay attention to the numbers, you would think that Beth sold about 3 or 4 times as much as Susan. So do you see how bar charts sometimes can be a little misleading? You have to pay special attention to this y-axis here when looking at bar charts, because it doesn't always add up. Like, that's about what Susan sold, and that's about that's about how much Susan sold, and that's about how much Susan sold. So it may not be 4 times as much if you just were to look at the actual area of this figure, but it is pretty close, and she definitely didn't sell 4 times as much. If she did, this number would be a lot bigger. It'd be 500 and something, or 600, no, it'd be 500 and something thousand, 600 and something, 700 something, I don't know. Do the math, you can figure it out. And she definitely didn't sell that much more. So sometimes bar graphs can be a little tricky, especially if you don't pay close attention to what's being given in the bar chart. Alright, here is an example of a stacked bar chart. I can say that I haven't seen lots of stacked bar charts. I don't do that much reading over data, but this would just be another way to represent a set of data. And so what this does, it takes what it says, the 2002 Winter Olympic medals, and it gives how many bronze, how many silver, and how many gold medals that each country received. So it's not like, you can see the total here was 35 for Germany, but 35 of those weren't gold. It's just this portion right here represents the number of gold, this portion the number of silver, and this portion the number of bronze. So that's a stacked bar chart. Since this does have a natural zero, or a zero starting point, this bar chart probably won't try to trick you like the last one did. That's something you always want to look at and see, if does it start with 0. Sometimes if it doesn't start with 0, it can be a little misleading. Alright. Another way to represent data is through a pie chart. Pretty early on in school, we learn about pie charts. And a pie chart is a graphical representation of qualitative data in which the circle represents the total pie available. and the slices are proportional to the amount in each category. That's a very important part. They are proportional to the amount in each category. Okay, and so I know that we've all seen pie charts from time to time, maybe just in your math class, I don't know. But it is one easy way to represent data. Let me show you an example of a pie chart. This example, I'm also going to show you what it would look like if it was given in a bar chart, and what it would look like if it was given in a pie chart. And this is all in your book. This is on page 79 in your ebook. So here you can see the data being represented in a bar chart, and then here in a pie chart. For me personally, seeing it in a pie chart kind of helps me understand. I mean, I know that I can tell that Social Security is the most, but here I can see the actual area here of this pie. Social Security is larger than, than this. But either way, you can really tell what the data is trying to show. It's not very misleading there. Alright, and so that finishes 3.3. 3.4 is on how to actually construct a frequency distribution. For quantitative data. Remember, quantitative or qualitative. Quantitative like quantity makes you kind of think of more numbers and number categories, or qualitative would be more labels and things like that. Okay, so qualitative data is more like the labels, so that was either a nominal or ordinal type of data, and quantitative, would be more like the other levels. What were they? Interval and ratio. That's right, very good. Okay, so I want to show you an example given in the book on heart rates of 50 students. You don't have to write these down. Again, they are in the ebook. We're around page 81 right now. If you have that pulled up on your phone or tablet or your computer, you can look at that. But there are the heart rates per minute of 50 students. So, if I was to ask you how many people's heart rates were above 97, well, then you would have to sit there and you would have to pick those numbers out. But if we were to take and represent that data in a frequency distribution table, we would actually go through and construct the number of classes. So that would be the first thing we would need to do. We need to figure out how many classes do we want to put in our frequency distribution. And so really that number, your book says, is arbitrary depending on the number or the amount of data that's available. You just want to kind of pick a good number. If you look and see here, the lowest is in the 60s or 50s. Look through there. The lowest is in the 60s. And the highest is in the 90s. Between 60 and 90. You probably want to pick 5 or 6, something like that. Like I wouldn't want to pick 2 because there's just too much difference between the lowest and highest. I wouldn't want to pick 30 because that would, could I come up with 30 classes? Maybe. But it's pretty much like looking at the data. If I come up with 30 classes, that's just too much. So you want to pick just some number that would kind of make sense to go with the data that you're given. Now, if this would have been a heart rate of maybe, I don't know, 500 people, and it ranged from 50 to 120, then maybe we would want to pick more than 5 or 6. Then maybe 10 would make sense. But given this data starting around 60 and ending around 90, I would say that 5 would be a good number. So first you pick the number of classes that you want to be in your set of data. Okay. After you do that, so we picked our number of classes. We're going to say our number of classes for this frequency distribution is going to equal 5. Then we need to figure out the class width. Well, what is class width? So I guess if we're going to figure out the class width, we need to know what we're talking about. Alright, so the class width would be the difference between the classes. So, do you remember when we were looking at up here? Well, it was up here. The difference here between these classes, we have to figure out some number to give us, that would give us the difference between the classes, or the width between the classes. Alright, and there's actually a formula that we can use to figure out the class width. Alright, so let me give you that formula. So this is if you were constructing your frequency distribution. The class width is the largest value minus the smallest value divided by the number of classes. Okay, so let's take our set of data. And let's figure out what was the largest value in that set of data. I see a 90. I see a 98. Alright, so I think 98 is the biggest number. So 98 minus the smallest value, 67, 65, 62. I don't see anything smaller than 62. So minus 62 divided by the number of classes. So we want 5. Alright, so that's going to be 36 divided by 5. Or $7.2. So 7.2, that's going to be our class width. Now, if you do have some type of decimal like that as one of your endpoints, that does make it a little tougher to calculate. Just meaning it'll take more calculations to do that, which is okay. I mean, it's just we may have to do a little work to figure out our values. So we said that the smallest value was 62. All right, and so how are we going to figure out the class endpoints? Meaning the smallest and the largest number in each class. So you see this frequency distribution here. Smallest and largest. Smallest and how do you actually figure those out? Okay. It really wouldn't make sense to start with the smallest number. There has to be some uniformity to it. So the exact value that you use, your book says again, is arbitrary. So what your book does, and there are some different methods you can go through to figure out that number. What your book does is it actually just selects a number. There are some methods that some books will say to use, but it would usually you don't select the smallest number. Okay. Generally, if it were me, I would probably not use a class width of 7.2. I would probably use one of about 8 or 9 or something like that, because it just would make a little more sense. The way that your book does this, it does use 7.2 as a class width. No, actually, let's see if it does. Yes, no, yes, no. No, it uses 10. So it just used something that would look a little better. 7.2 is okay, but using something like 8, 9, or 10 would also be acceptable. So instead of me just keep rambling on and saying the same thing over and over, let's just go ahead and construct us, and we'll try to do this as fast as possible, construct us a frequency distribution. Now yours may not look like mine, like if we were doing two different ones, because you may choose a different class width, and you may choose a different starting point. So what I'm going to do is I'm just going to choose 10. That would look good because I like counting by 10. And then we have to pick some starting number. Well, if the smallest number is 62, how about we just start at 60? So let's say from 60 to, now if I use 10, then that would be to what? 70. So then my next class would start at 70 and go to 80. No, 71. I'm trying to, we need to keep this uniform. So if this has to go to 71, I guess that would be okay. A lot of times decimals are used so that you don't run into that problem, because now this class width is 9. So how about we say, and this is just so that we won't run into that problem, let's say 60.5 to 70.5. So do you see how this would this would help us not run into that problem that I'm talking about? And then this one could be 71, let's see, this could be 71.5 to, I'm trying to figure out a way. This is just not working with the tens. But let's just keep going. Let's say 71.5 to 81.5. See, because we're leaving out a whole number there. But we still have, what if we had 71? Would we be able to put that in either of our classes? So I'm just worried that we're going to leave something out. So there's 70, there's 70. Those would both work. But if we did have a 71, then it would be left out.
Why can't you end with 70 and start the next line with 70?
Because then 70 would be in both classes.
Up to and after.
Up to and after. So 270 and then 72. What would make sense, I guess, would be if we went 270 here and then 70.5 here. That would mean after 70, right? So that would make sense. So then this one would go to 80, and then this one goes 80.5 to 90. This does mean we're using a class width of 9.5, but it makes, with the data that we have, it kind of makes sense to use the decimals there. So we're just using 9.5 every time. So 90.5 to 100. We said that we wanted, that's 4 classes, so then the next class, the 5th one, would be 100.5 to 110. So that is one way. You know, if I ended with 70 here and I started with 70 here, then that would mean that 70, if there was a heart rate of 70, would go in both classes. There has to be a way to kind of filter that out. I'll show you how the book does it, but they use hundredths on one end and they use tenths on the other end, so it's a little confusing as well. But we're kind of making our own here, so it doesn't have to look exactly like the book would have. And this is heart rates. So now what we have to do is we actually have to tally the number of heart rates in each class. This is going to be the number of students. All right, and what I would do, and this is if you're constructing your own frequency distribution, I would first tally maybe with slash marks, and you'll see what I'm talking about in just a second. And then I would go back in and write the number or the percentage or whatever. So here's what I would do. So I'm going to go through each data, each piece of data, and I'm going to put a tally mark in the class, in each class, if it belongs to that class. So 77 would be in this class. 84 would be in this class. And 79, 90, nope, 90 is in this class, right? 67, 84, 82, 74, 69, 81 would be here. 94, 68, 65, 86, 78, 79, 83, 83, 84, 82, 93, 80, 81, 80, 62, 98, 77, 83, 82, 80, 82, 73, 77, 79, 81, 70, 72, 85, 84, 80, 83, 77, 80, 70, 75, 74, 85, 87, 79, and 88. Alright, so that was our tallying system that we use. That's usually the best way to kind of go through if you're just looking at raw data and you don't have something to do it for you. So then I'm going to go back and I'm going to erase these tally marks and I'm going to put the actual number there. Alright, so this was 7. This was 19. This was 21. This was 3. And this was 0. And if we add these numbers up, we should get 50. Probably want to do that to make sure. So 16, 17, 18, 19, 20, 0 carry the 2, 50. Yes. Alright. So this is what our frequency distribution chart would look like. Of course, we could draw our lines in here. You know, could make a little table here. Alright, and since we chose a class width of 9.5 to help kind of alleviate some problems we would run into, you know, it may not be the same as what the book used. It's not. They didn't start with the same number, so that means they didn't end with the same number. Here's what the books table looks like that they come up with. You'll see, I mean, it's kind of similar to ours, but not exactly. Alright, let's see. Make it a little bit larger. Okay. So, you can see that they started at 57.51 and went to 67.5. Alright. And then they constructed their frequency distribution. Now that this is just a regular frequency distribution. We could make this something called a relative frequency distribution, and it wouldn't take much more work to convert ours over to a relative frequency distribution. But of course, to do that, we would have to know what is a relative frequency distribution. And the relative frequency distribution of any class is the number of observations in the class divided by the total number of observations. Okay, so that's how you find relative frequency. The number in the class divided by the total number of observations. And if you want to write that down like a formula, it's the number in class divided by total number in observation. If you think of it, it's really just like a part divided by total. Okay. Sometimes you may see that as a decimal. Sometimes you may see that number times, say this, the decimal times 100 to make it a percentage. So if we wanted to do that for the one that we come up with, I'm just going to add another column. This column would replace the column we have here that we made. I'd rather do it on ours than theirs because we actually got to work and do ours. We worked really hard, so let's use it. Again, the numbers that I write down here would be the numbers that would replace these. That would make it a relative frequency distribution. So what you want to do is you want to take 7 and you want to divide it by the total number, 50. Okay, and then I'm going to round to 2 decimal places. I'm going to do that in a calculator. 7 divided by 50. Alright, so 0.14. Now you may see this written as 0.14, or you may see 14%. That means the same thing, right? All right. Now let's do 19 divided by 50. 0.38. 21 divided by 50. 0.42. 3 divided by 50. 0.06. And the last one here, of course, is 0. 0 divided by 50 is 0. So instead of just being a instead of just being a frequency distribution, then we could call that a relative frequency distribution if we didn't have these numbers here. And again, I've already told you, but sometimes you may, instead of seeing the decimal, it may just be written as a percentage. Alright. The last type of frequency distribution that we're going to look at today is the cumulative frequency distribution. Alright, and the cumulative frequency distribution, think if you hear something is cumulative, what do you think about? Maybe adding it up or summing it up or something like that. If something is cumulative, that means that the sum of the frequency of a particular class So a cumulative frequency distribution is the sum of the frequency of a particular class and all preceding classes. So if something is cumulative, that means that from one class to the next, we're just adding and keeping a running total. Okay? So let's go back to our table that we made. Now I'm going to add another column here. This column that I'm going to put on here would take the place of this column would take the place of this column. So of course the decimals, this would be for the relative frequency, that wouldn't be there. And this new column, using these classes that we made, would look like this. So for the first class we have 7. It's still 7. Alright, the next class would have a cumulative frequency of 7 plus 19. So 7 plus 19, that's 26. Alright, it's a cumulative frequency, so it's like we're just keeping a running total as we go. So the next class would be 26 plus 21. So that would be 47. The next class would be 50. And then the last class would be 50 because the last class has nothing in it. With nothing being in the last class, it would be okay just to get rid of it completely. But since I decided on 5 classes instead of 4, That's why we have the 50 twice. So normally you wouldn't see that. Let me show you an example really quick. Of a cumulative frequency from the book. So they give the frequency and the cumulative frequency just so you can kind of understand how they got the numbers. Alright, so here are their classes. Here are the frequencies, and then you can see the cumulative frequency. The first class is 3. The next class is 3 plus 13, so you get 16. The next class is 16 plus 29, so you get 45. The next class is 45 plus 4, you get 49. The last class is 49 plus 1, it's 50. Now, if you took that cumulative frequency table and you figured out a decimal for each one of those, part over total, then you would have a cumulative relative frequency distribution. So if you took your relative frequencies and then you added each one, you started with 0.06, and the next one is 0.06 plus 0.26, the next one is 0.32 plus 0.58, and so on and so forth. That's called a cumulative relative frequency distribution. So it's the same thing we did before, except with decimals instead of whole numbers. And these decimals are the relative frequency, but if it's cumulative, that means that you add the previous number to what you have, right? So this 0.90 is 0.58 plus 0.26 plus 0.06. All right, and that ends 3.4.